So welcome. This is my last lecture. I'm sure you are very tired. It was a very dense week. And so today I will be producing an introduction to quantum computing. So you will be learning about something awesome, okay? And also something very weird, the quantum computer. There is no background on quantum required, but you have a background in quantum by now, so it should be easier for you. This is meant to be an introduction. So here's a brief overview of the goals for your learning. Understand what a quantum computer is and what they are good at. Learn the fundamentals of how to code in Python. Understand quantum superposition and how it relates to quantum measurement, explore aspects of quantum entanglement, program a quantum algorithm in Python using IBM Qiskit. Okay? So what you need to set up some accounts before we start with the lecture. So first of all, there are for you some codes that were prepared on Scratch. This is an online tool and it's called Scratch. Scratch is an easy to learn computer programming language. It's funny and fun. That lets you write computer programs in a visual platform. You will need to make a Scratch account. Go to the registration webpage right now. It's https Scratch MIT-EDU job and join Scratch. So I'm ready. Please do that too. You have to. So did you set up that account? Are you setting it up? It will be very important for you. Please register and join Scratch. Here is the address. It will be important. Here, good job. So are you ready? All right. The next account that you need is a Google Colab account, setting up a Google Colab. All you need to do is, yes. Yes, we can, but I would appreciate it a lot when we can start on time. All right? Okay. The next account, as I said, is the Google Colab. And all you need to do is you need to have a Gmail account to have a Google Colab. And if you do not have one, please go simply to Google and sign up. Once you create an account, you can open Google Colab. Here. It looks like this. https://research.google.com notebooks intro title. Have you set it up? Do you have a Google Colab account? I think most of you do anyway. You can collaborate with your friends, with your advisors, with your mentors, with your colleagues, with people that is very unlike a lot. So next, sign up for IBM Quantum Account. So go to IBM ID. It looks like this. And create an IBM ID account. So fill the page out, please. Ready? Okay. Did you set it up? How many are done? The rest is still setting up. Okay, let's wait a little bit. Guide the notes I will help. We're guiding them. We should check my plot. IBM Quantum Experience allows us to use real quantum computers. Okay. So it's a really nice service by IBM. Company which I like personally a lot to take care of us with education and outpatient service. And we will have a speaker from IBM today talking about protein structure prediction microbiome. So, all right, I'm starting. Are you done with setting the accounts? So, why quantum computers? When it's natural, when humans encounter problems, they often use tools to help to solve them, right? Computers are one of the tools that we use. They are great at mathematical problems, repetitive tasks, and searching large sets of data like moving. However, in the same way that a hammer isn't very good at putting in a screw, a computer isn't always the best tool to solve other problems. This is why scientists and engineers are seeking new ways of making computers that will let us solve a wider variety of problems. One of these technologies is quantum computers. So how many of you are familiar with the Haber-Bosch process? What is it? Yes. Fertilizer. Yeah, very good, thank you. So the next problem that quantum computers can help us to solve is a chemical process called the Haber-Bosch process. This process is used to create ammonia that will be used widely as a fertilizer. Okay. Ammonia is a critical chemical that helps us to produce more food for larger human populations. The Haber process uses very high pressures and temperatures to create ammonia. Creating these high pressures and temperatures requires a lot of energy. In fact, the Haber process uses about 1 to 2% of the entire world's energy supply. That's huge. That's a lot. So this raised the question that to seek other ways to create a fertilizer without using so much energy, right? How can we do that? So there is a humble pea plant, actually, that does it by itself. It uses a special molecule called nitrogenase to create its own fertilizer without ever using high temperatures or pressures on this planet. It's existing. So this is the humble pea plant, right? And this is the nitrogenase. It's iron and a cofactor, and it has cysteines and histidines attached to it. So how can you solve that with classical computers? Can you solve that using classical computers? So, unfortunately, scientists have not been able to understand how the nitrogenase molecule creates fertilizer. Okay. Remember that molecules like the nitrogenase in the pea plant are described by quantum information. Part of the reason why we have not yet been able to understand nitrogenase is that we are trying to understand quantum information using classical technologies. It simply is not the right tool for the job. So, a better idea might be to use a quantum computer to understand quantum information. This is just one of the reasons that quantum computers were developed. In fact, there are many more applications for this idea of quantum simulation using a quantum computer to understand quantum things like atoms and molecules. One important one is the discovery of new medicines. The molecules needed for medicines can be very complicated, and having a quantum computer would help us understand them better, potentially leading to life-saving discoveries. All right. How many of you are familiar with the traveling salesperson problem? Oh, yes, you took my class. What is it? Yeah.
Problem. There's a salesman, and he have to visit different cities to sell something. And he have to find the shortest way to visit the cities.
Most efficient.
Yeah. And it is impossible to get an optimized way.
Using classical computers. Yes.
A short spin problem?
Well, you can use Google Map for a short spectra, but what about when you have to visit 10,000 cities? Or 10,000 places?
It's too much.
How can you do that? Or 1,000? So, salesperson, traveling salesperson, have you ever heard of cafes or restaurants that give out free pancakes or burgers to people on their birthday? So when you have a birthday in Canada, most of the places, and some places also in the United States, give free burgers. So let's assume it's your birthday, and let's assume that you are in Canada or in the United States. So, and you're a freebie lover, so you have marked down more than a dozen places where you can get free stuff on your birthday on the map. Okay, and this is our map. How you can make sure that you will manage to visit all those places in a single day? You somehow need to plan things out to stop by all these places as fast as possible, right? What we described is a form of very well-known problem in computer science called the traveling salesperson problem. The traveling salesperson is an optimization problem about someone who wants to sell some goods at multiple cities. What they want to figure out is the shortest and fastest way possible for visiting all these cities one after another. So the map here, you can figure that out by yourself, right? You can plan here, but because it's just few points, right? Few restaurants that you want to visit. You can plan that by yourself, or you can, if it's too much for you, you can use a classical computer to plan that out. But this may not seem like a difficult problem for a small number of cities, but what if the person needs to visit 50 cities, or 100, or even 10,000? As the numbers of cities increases, finding the optimal solution becomes more and more complicated, right? So a classical computer is able to easily find the solution for 10 to 12 cities. But what will happen when the number of cities increases? Well, the salesperson may have to wait for their whole life or longer to get the optimal solution from a classical computer. By that time, they most definitely don't need the answer anymore. So, we had quantum mechanics and quantum chemistry a little bit, and I think you understood a lot. And you know by now a lot, and the slides will be uploaded. Will be uploaded today, right? And you can read the slides and study the slides and study from books and other resources. So what Richard Feynman said is, I think I can safely say that nobody understands quantum mechanics. I don't agree with that. Do not keep saying to yourself if you can possibly avoid it. But how can it be like that? Because you will get down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can go. Albert Einstein. I have thought 100 times as much about the quantum problems as I have about general relativity theory. Needs for. If quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Okay? So, when it comes to classical versus quantum, Sir Isaac Newton, Galilei Galilei, and many other scientists through tried to explain the world around them by finding rules that could capture and predict its behavior. They contributed to the old way that humans used to explain the world, which is called classical physics. Classical physics is still studied and used because it has been successful at explaining things on large scales. However, there are incidents that classical physics cannot explain, like the Haber-Bosch process, right? Quantum physics is the part of modern physics that talks about very, very small things in our world, like molecules, atoms, and subatomic particles, like electrons and protons. All our surroundings are made up of molecules and atoms, so in a way we can say quantum physics describes everything at a fundamental level. This is where classical physics breaks and cannot give us a solid explanation. With all these said, quantum physics still has a long way to go, and there are yet more things to be discovered and explored in this field. Predictions of quantum mechanics have been shown to be extremely accurate through experiments. There is a great match between theory and experiments here. Quantum physics is not easy to comprehend, but we have been able to use it in a variety of ways and make useful devices that have a great impact on human life. So when it comes to the scale of quantum objects, the things we are most familiar with, like books, cars, food, and so on, all are described by classical information. Where in the world can we find quantum information? Quantum information is contained in qubits, okay, which are the quantum version of a classical computer bit. How many know what a bit is? Things that are very cold or very small are described by qubits and can store qubits. This includes some of the weirdest things out there. For example, superconductors can be used to store qubits. Single atoms or even single electrons also store qubits. We will have a chance to explore some of these topics here today. So, what is quantization? Any idea what that means? Quantization of light. Huh? Yes?
In terms of light, it's be considered as a wave, but quantization. It's instead of a continuous wave, it's acting as a particle. So
Quantize. Right. Very good. So until the late 19th century, light was considered to exhibit only wave-like properties, right? As are evident in phenomena such as interference, diffraction, refraction, etc. The wave theory of light was the basis of the entire classical electromagnetic. However, one peculiar experiment called the photoelectric effect was not understood by scientists using the wave theory of light. There are a large number of free electrons that are present on the surface of a metal, right? A metal surface has electrons on it. When light of sufficiently low wavelength, what does it mean? When it's low wavelength, what about its energy? Higher energy, right? These free electrons are ejected from the metal, right? This is the photoelectric effect. It was discovered that if the wavelength is too high or the frequency is too low, then these electrons are not ejected, right, as expected, even if the beam of light has very high intensity. This was very counterintuitive because according to the wave theory of light, which is classical electromagnetism, the energy of emitted electrons should be proportional to the intensity of the incident light. To explain this, the photon theory or the particle theory of light was formulated by Einstein in 1905, for which he later won the Nobel Prize. He theorized that light is made of packets of energy called photons, right? A photon can be thought as of a particle of light. When light is considered to be a wave, it will have wave-like properties such as the wavelength lambda. Each particle of light or a photon will have the energy equal to h times c divided by lambda. H is what? What is h? Light constant. What is c? Speed of light. And lambda is the wavelength. Yes. So, for any given wavelength lambda, the energy of light is an integer times hc divided by lambda. Since the energy of light can be varied only in the quantum of hc divided by lambda, the photon theory of light is called the quantum theory of light. A quantum, what does a quantum mean? It's the smallest packet of energy, right? Of light is called a photon. When light is incident on a metal surface, the photons of light collide with the free electrons and the electrons are ejected from the metal surface. This phenomenon is the photoelectric effect. The electrons will only get emitted from the metallic surface if the wavelength is low enough, right? For low frequency or higher wavelength, the electrons may not be emitted, irrespective of the intensity of the beam of light. Strong beams of light toward the red end of the spectrum might not be able to eject electrons at all, while weak beams of light toward the violet end of the spectrum would produce a higher and higher number of electrons. So, here it is. Assume this is our metal surface, and this is how the electrons can be ejected from the metal surface. So when it comes to quantization of energy levels in hydrogen, how many of you heard this? Quantization of energy levels in hydrogen. So consider an electric bulb which gives off white light when heated. If this light is made to pass through a prism, it will result in spreading of components of visible light, right? Such as that in a rainbow, to result in a continuous spectrum. If hydrogen gas is enclosed in a steel tube and is heated to high temperatures, electromagnetic radiation is emitted. Electromagnetic radiation is basically a combination of visible as well as invisible light. When we pass this radiation through a prism, we would see the different wavelengths emitted by hydrogen. Instead of a continuous spectrum, we would see only specific wavelengths, resulting in a discrete spectrum. No matter where this experiment is conducted, hydrogen spectrum always has only these specific wavelengths. So what does it mean? In 1913, Niels Bohr provided an explanation for observing such a discrete spectrum of hydrogen. He proposed that electrons revolve around the nucleus of an atom in very specific fixed orbits. An electron revolving in an orbit would have fixed energy. If the electron jumps from a higher energy to a lower energy, it would do so by releasing a photon of energy h times c divided by lambda. If the electron wants to jump from lower orbit to a higher orbit, it would absorb the energy h times c divided by lambda. This would result in the observation of discrete spectrum, as electrons can only absorb or release specific quantum of energy. So here is the electron transitions for the hydrogen atom. You have the Lyman series, Balmer series, Paschen and Brackett series. Okay. The Lyman series here, it can be from here, En to En is equal to 1. The Balmer series is to N to equal to 2. What is N here? No.
It's the word.
It's a quantum number. It is related to quantum, right? Okay, I want you to check that out. Before I continue, I will come to that point again, but here is the double slit experiment. How many of you are familiar with double slit experiment? Do you know what that is? What is it?
Double slit and as mentioned, the shorter wavelength light is used
Mhm.
in the experiment. And of course, at that time, they thought it's acting as a wave, so the light waves has to go in a certain way when you use a double slit, but it's they saw a result that cannot be explained with the wave behavior of the light, so they came up.
Okay. So it is time to put our experimental hats on now. We will try to understand some interesting properties of quantum objects via the whole experiment. After understanding the experimental setup, I will ask you questions that follow to discover the weirdness of quantum mechanics, and you will see that by yourself. Consider an experimental setup that will be shown in the next slide. There is a source which could eject classical objects like a tennis ball, okay? Waves or quantum objects in random directions. That's the source. Next to the source, there's a solid wall with two openings that we call slits in English, through which any of the objects could pass. Then we put a screen that is placed after the double slit wall. If any object hits the screen, the place gets marked. Okay, that's the experiment. Therefore, it is possible to find out where exactly the object hit the screen. If a wave-like object hits the screen, then the position of peaks of the wave get marked. So this is my double slit experimental setup. All right. So I have a table tennis ball or balls in my source. And I start in my source creating this table, then tennis balls, and it goes to the double slit wall and then to the screen. Would you see random or interference like characters on the screen? Tennis balls. Is tennis ball a classical object or a quantum object? That's special. So would it be random or interference? Some of you said interference.
Because we cannot fix the slit directly, so short only will be.
It goes through the slit, it hits the screen afterwards. So is it a random or interference? That's the question. What would you say, Giles?
For the principles, it's a classic object, so I don't need you.
So let's say you have light waves. Would it be random or interference? Fine.
I don't know the time.
You do these experiments at home, you know.
It behaves differently. Some
What about single photons? That experiment at home would be difficult. But you can do that with tennis balls and then decide if it's random or interference.
I think it should be random.
Single photons are random, you say. What do you say, Jai?
Whether it's
What about electrons?
Next one. Okay.
What would you say, Melissa? What? All right. So these questions will appear in the test. So wave particle duality. The thought experiment we carried out made us realize some very interesting things about the classical and quantum world, right? The double slit experiment shows that quantum objects can have wave-like as well as particle-like properties. The table tennis balls hit the screen in a random manner as expected. Haven't you played with balls when you were little kids and throw it on the wall and then it's never interference? I've never seen interference. It's only random, right? So the light waves, the table tennis balls hit the screen in a random manner as expected. Things implies a particle-like behavior for classical objects. The light waves showed an interference pattern on the screen after passing through the double slits. When single photons or electrons passed through the double slits, an interference pattern was observed. This would imply a wave-like behavior for quantum objects. If there was a detector, Jahid and Melissa, placed on one of the slits, electrons or photons would now hit the screen randomly without showing any interference pattern, right? It depends on the detector. So this means that they exhibit particle-like behavior if we try to find out which path the electron or photon took before it hit the screen. What does it mean? So it means we have a double slit, right? 1 and 2 slits. So it can take path A or path B. If an electron or any quantum object passes through the double slits and reaches the screen, which path did it exactly take? Path or path B? Is the question. These are logical questions.
Both.
Both. Why?
One.
Why?
Why? Because of superposition.
Very good answer. So the answer is that the electron was traveling via both paths at the same time. This is the quantum magic of superposition, as Malva said. However, things change if you place a detector, right, to find out which path was actually taken by the electron. In this case, the electron suddenly starts behaving normally like a particle. The act of measurement changes the way the electron was behaving. It seems as if the quantumness of the electron is mocking the observers. We will keep coming back to the terms superposition and measurement and again throughout the course today. If this was confusing for you, do not worry. This is a topic that has baffled scientists for over a century now. All right. Perhaps the concept of superposition is best explained by the physicist Schrödinger and his cat. So quantum wave functions, classical determinism. Classical objects follow rules of classical physics, such as Newton's laws of motion. Consider a car moving in a straight line with a uniform velocity v. We define a quantity called momentum by T is equal to mass times velocity. So, where m is the mass of the car, right? Classical physics tells us that at any time t, the car would have traveled a distance that is given by x is equal to v times t, right? Velocity times time. So, it's kind of deterministic, right? How the car travels. So in other words, if you were to conduct an experiment that allows you to measure the momentum of the car at any time using some knowledge of physics, you would be able to calculate the position of the car at any given time. Alternatively, if you know where the car is at any time, you would be able to calculate its momentum. Additionally, we can measure both position and momentum of the car at the same time. There are no surprises here at all. The motion of the car is completely deterministic. So is classical molecular dynamics. Now, when it comes to Schrödinger's equation and the uncertainty principle, we had these on Wednesday, but let's talk about it a little bit more. We looked at the wave-particle duality of electrons in the context of the double-slit experiment. If we think of electrons as particles, we can assume that they follow some kind of equations of motion, similar to the way classical objects follow Newton's laws of motion. However, we need to be able to account for all of their wave-like properties as well. The equation that captures this essence of quantum objects is the Schrödinger's equation. It gives information about all quantum mechanical properties, for example, quantized energy levels of a hydrogen atom. Quantum objects follow rules of quantum mechanics, such as the ones described by Schrödinger's equation. So what quantity does Schrödinger equation actually talk about? Schrödinger equation describes the wave function, which includes the entire information of the system, right? Of quantum objects. Now, these wave functions are related to the probability of finding a quantum object at a particular position. So it's not like the car. It's not that easy. It's not deterministic. This means we cannot say with certainty where the electron or any other quantum object will be at any given time. So it could be between A and B, for example. I shaded that area here. So it could be there, for example, okay? So let a quantum object be described by let me see how I can get rid of this. So a quantum object is described by a wave function, as you know by now, right? The figure depicts the probability of finding the quantum object at any point along the x direction here. Just a second, I can go back here. Along the x direction here. And the shaded region represents the probability of finding the quantum object between points A and B on the x-axis. Note that this just depicts the chance of finding the quantum object in the shaded region. There are no guarantees here. It can be anywhere. This is in sharp contrast with classical physics, where it can determine the past, present, and future positions of an object simply by looking at some equations. So quantum mechanics is not deterministic like classical mechanics. In the example of the car, we talked about how the position and momentum can both be simultaneously measured for classical objects. Quantum objects, such as electrons, will also have properties such as position and momentum. Now, similar to the car experiment, we can take up fancy detectors and try to measure the position as well as the momentum of the electron. However, if we pin down the position of that electron, we will be unable to measure its momentum, irrespective of how accurate our detectors are. Moreover, if our detector determines the momentum of the electron, then we will lose any information about its position. It is as if the electron is playing an eternal game of hide and seek with us. Okay? Heisenberg's uncertainty principle dictates that the more precise it determines a quantum object's position is, the less precise is its momentum, and vice versa. So we discussed that for a wave function, C given by Schrödinger's equation, the position is not a determinate quantity. It is given by some probability distribution, such as the one shown in the top panel of the figure before, right here. So then the shaded region represents the probability of finding quantum objects. However, this is all just probability. We have not actually measured the position of the quantum object. When we actually use our experimental apparatus and measure the position of the electron, we may find it at any of the points along X based on the probability distribution in the panel. Recall that higher the probability, higher are the chances of finding the electron at that point along the X direction. So let's say we conducted a measurement and this is the result. So the electron is found to be near point C. Notice now that the probability distribution is now centered at point C. This means that we have now determined the location of the electron to be at point C, which reduces the probability of finding the electron at any other point on X to 0. So where exactly was the electron just before it was measured to be in state C? Can you answer that question? What do you think will happen if we measure the position of the electron again? Will it still be at point C or any other point, A, B, and so on? How do you know?
It's extreme non-like.
As we cannot predict definite.
What do you say?
Yeah, just probably check the probability.
Okay, I'm asking also other students. What do you say? So, yes, and that group. Melissa, Jai, what do you say?
So the electron was in that area or any kind of area under that curve, and it has a possibility to be at point C before the measurement.
Mm-hmm.
After we measure, we break position and we know that it's in state C.
Mm-hmm. So, but the question is, what do you think will happen if we measure the position of the electron again? Will it be C? How do you know? Can it be C? Yes. There is a probability, yes. Yeah. That's the answer.
But extreme.
Well, there is a probability.
That's what it's.
How do you know?
Statistic, it's different. Like, if I just rule the
It's
Point-
not static,
it's-
right? It's dynamic. Electrons are dynamic. So it's not static information here. So let me go into that. Where exactly was the electron just before it was measured to be in state C? In the example before we actually measured the position of the electron, we were not sure where exactly the electron was, right? We say that this electron is in a superposition state of all possible points that are predicted by the wave function. The probability of finding the electron at any specific point is determined by the wave function. In the example of the car, we could exactly say where the car was 1 second before the measurement, right? In classical physics, you can say that. We could also determine where the car will be 1 second after the measurement of its position, right? Let's say you measured where it's located, the car, you can use x is equal to b times t, and you can measure the position for 1 second after, again, or you can determine. But what about the electron? So where exactly was the electron located before we measured its position? The honest answer is that nobody knows. The probability distribution just says that the electron could be anywhere in a region, with some regions more favorable than others. The topic of where the electron was prior to measurement has been debated for over a century now and has puzzled the likes of Einstein, Bohr, and many other great scientists. So, what do you think will happen if we measure the position of the electron again? Will it still be at point C or at any other point, A, B, and so on? Was the question. Once we perform a measurement to determine the position of the electron, we say that the wave function has collapsed to that specific position, in this case, point C. Now, even if we perform repeated measurements on the same electron, we will still find it only at position C. All the previous information about the probability distribution has been erased from its memory. Okay? This section just gave a preview of the concept of superposition and measurement in quantum mechanics. We will see these two concepts again when we study qubits in the next section. You will understand it better and you will perform some experiments on Scratch 2 and IBM computers too. There will not be a dealing directly with the position or wave function of electrons or any other material used for the qubit anymore. Instead, we will mainly be using a very intriguing quantum mechanical property called the spin. And you are familiar with the spin is alpha and beta. We had it already, let's say. So, bits. We live in a time that is often called the information age, right? This is because we share and use an enormous amount of information in our lives. Books, memos, videos, tweets, and texts are all forms of information. Information can be in various forms. Even a coyote's howling to let others on their pack about a potential danger is kind of information, right? So less than 100 years ago, people mostly relied on sharing information on paper or by word of mouth. This is no longer the case. Most of the human's knowledge is now being shared and spread using computers. This raises a question. How are all these different types of information presented, stored, and shared using computers? In today's computers, information in books, memos, tweets, and videos can all be stored as zeros or ones, right? We call these zeros and ones bits. Bits can join each other and make series of bits to represent the information we want. The information which is stored using a series of bits is called the binary information, right? So when it comes to quantum bits, the information you are familiar with, the information in text, videos, and pictures is one kind of information class called classical information. However, not everything is accurately described using classical information. This is where we require quantum information. Remember that classical information can be built out of units called bits. Similarly, quantum information is built out of qubits, which are quantum bits. In short, qubits. In this section, we will explore what qubits are and how they are different than bits. To begin exploring qubits and quantum information, it will be useful to have a picture that represents a qubit. Recall that bits can have two states, which we call 0 or 1. We can also label the two states with something else, though, with down and top, or green and red, right? Or blue and green dots, like here. So zeros are green, ones are blue. All right, I can call it also green and blue. I don't have to call it 0 and 1. All right. So another choice we can make is to label bits with up or down. Are you familiar with this picture? How many of you are? One person, 2, 3. A key difference between bits and qubits is that they can be in more than just two states, the qubits. Using the arrow example, instead of just up or down, they can be in any direction. This is the power, right? This is the power. Classical bits can be stored as 0 or 1, as true or false, as blue or yellow, dot, or high or low voltage, and so on. Likewise, there are many different ways to store a qubit. Some examples are using photons, a particle of light, using superconductors, or using the spin of a small particle like an electron. Spin is a property of particles, just like mass and charge, that we can determine using magnets, right? We can visualize the spin using the arrow picture. Yeah. As a starting point, we will look at 4 different states of qubits that can be existing. We will label these by drawing arrows in 4 different directions, like this: up, down, and then your right and your left. We will call these up, down, left, and right. By understanding these 4 quantum states, we will find out that qubits are strange yet very powerful. So, how many of you are familiar with the Stern-Galler-Hexagon? I want you to go to this page now. You all have a spreadsheet account. Let's perform this exercise. If you took the task. It's on Scratch. Go to this address and then start making the experiment. You like it?
It just,
You can try it too. So you have a source, all right? This is the box that will shoot spins out. The spins have a qubit stored on them, like we discussed here. The qubits can be up, down, left, or right. And then we have a magnet. This has one place atoms can go in and two places they could come out. You can turn the magnet using the button to its left. Start out with the magnet set straight up and down, and then you have a blocker. This is blocking one of the places the atoms can come out of the magnet. You can switch the blocker position by selecting up or down in the top menu. What do you see? It's not like this, right? It can go any direction, actually. In classical computers, the bits go with 0 and 1. Here, you have 4 cases, but it can be in any direction, actually. Do you like it, Sammy?
Sert. Şu çocuklara göstersek. Hepsi falan. Just your head to yourself. Open this size. You just type the website. Yeah. No. You just type the website.
Okay, you can start the discussion. What did you observe? Did you do the experiment? So, I have a heavy German accent because I was born and grew up in Germany. So sorry for that, but these were German scientists. So,
but I thought for the simulator, I'm gonna expect like any spin I choose is just gonna go anywhere, even if I log in.
keep it for yourself. Real simple. Do more experiments like this.
Yeah. Beğendin mi hocam?
Hı?
Rastgele. Aynı şeyi bile deniyorum. Bir oraya bir oraya gidiyorum. Pattern yok.
Nasıl gidiyorsun?
Herhalde 100 kere tekrarlamam lazım.
There's a pattern.
Evet.
There's a pattern.
Yukarıdan bakmazsak yukarıdan yer varsa geçiyor.
Hı.
Diğer türlü geçmiyor. Çarpıyor. Hafif.
Bu mu sonucu yani? Böyle. Sen bu dersi almış mıydın benden?
Gayet destek gelmiştim hocam dersi.
Evet. Bunu yapmıştım daha önce. Evet İrem. Pattern, observations. What are your
İlkinde
experimental
istediğin yerden
observations?
gidiyor da ikincisinde rastgele. Öyle gidiyor.
If you turn the atom like in this direction and the magnet in this direction, it will go always on the right side. always. And the buckets.
So there's 1 year observations from the experiment. Deney yapmak istiyordum ama size seni. So, I'm waiting for your observations. Sıkıldınız mı? Saat mi? 11:30.
Evet, bayağı işte.
11:30.
Yani 28 geçiyor. 2 dakika.
O zaman burada bitirelim. Öbür derste devam edelim. Ara veriyoruz, değil mi? Arada. Okay, we have to stop here. We have to stop here. We will continue after the break. So, you're welcome. So after the break, I will continue with quite completely, and then we will go into alpha and send.